First, I would like to thank the organizers for giving me the opportunity to present here my work. Today, I will talk about how we use the local measurement probe, a SQUID, to directly image and measure thermal fluctuation near the superconducting transition. So, superconductors can be characterized in several ways, and one of these is by the sharp transition they go through at the critical temperature, where the resistance drops to zero and the diamagnetism sets in. However, thermal fluctuation broadens this transition, and the presence of thermal fluctuation is well understood, and their thermodynamic properties are also well understood, but today I would like to focus on the local aspects of these fluctuations. So the question is, why in the first place going local? So the local view can actually give us additional understandings of the physics involved in any physical system. For example, the modulated superconductivity found on various superconductors deposited on strontium titanite. Here you can see scanning SQUID images of the diamagnetic response of various materials deposited on STO, and as you can see, the diamagnetic response is modulated in a stripy configuration. These modulations were found to be caused by the domain structure of the substrate, and they actually help to correlate between the electronic properties and the structural properties. These images also demonstrate that the scanning SQUID is a great tool for measuring the diamagnetic response, and that it is sensitive enough to see small modulations in the signal, making it an ideal tool for measuring local superconducting fluctuation. So the question is, what will we see when we use the scanning SQUID to image these fluctuations? So I will first start from giving you our take on scanning SQUID. And as it was mentioned at the start of the conference, SQUID stands for Superconducting Quantum Interference Device. Basically, it is a superconducting loop with two Josephson junctions. And this makes it a very sensitive magnetic flux to voltage converter. To gain a better spatial resolution, we extend a small loop out of the big loop and cover the rest of the big loop with another superconductor. This way, a flux can only thread only through that. Only through that micron-sized pickup loop. This all design sits on a silicon chip, so we can also add a local field source and other on-chip electronics. At the end, we polish the silicon chip, bringing the pickup loop as close to the edge as possible. And all in all, our SQUID looks like this. This is an optical image of our sensor with a zoom in on the pickup loop and on the field coil. So with our scanning SQUID probe, we can perform several types of measurements simultaneously. Today, I will focus on two, which are magnetometry, where we measure the magnetic flux generated by the sample, and susceptometry, where we measure the response of the sample to an applied magnetic field. But in general, we could also use the SQUID to map current distribution or electronic states in different temperatures, applied fields, or applied stress. So in magnetometry, we bring the pickup loop close to the sample. Okay. We bring the pickup loop close to the sample. The flux going through the pickup loop is converted into an electric signal. And by rastering the pickup loop over the sample, I can record the magnetic flux as a function of position. We then present this data as a topographical map where the color represents the amount of flux measured at every point. And here you can see a vortex as it was imaged from one of our samples. So in addition to the flux measured from generated by the sample, we can measure flux that we ourselves generate, and we do this with the field coil. By applying an AC current in the field coil, I can generate a magnetic field that my pickup loop senses. And far from the superconductor, the only magnetic field that my pickup loop senses is the one generated by my field coil. But as I bring the SQUID closer to the sample, the Meissner response will create a stronger screening field, and this will create an increase in the total signal measured. The signal will rise until the SQUID touches the sample, and the difference between the signal far from the sample and close to the sample tells us about the quality of the superconductor. So usually the diamagnetic response is being described in negative values, but today I will use positive values just to emphasize that the stronger signal means stronger superconductivity. Also, because the signal far from the sample does not depend where on the sample the SQUID is located, I can raster my SQUID over the sample and record the susceptibility as a function of position. And these measurements I can do in different temperatures and record the evolution of the susceptibility as a function of temperature. And for example, here you can see different susceptibility measurements as the SQUID approaches the sample at different temperatures. And what we can see is that as we increase the temperature, the susceptibility signal decreases. Above the critical temperature, there is no change between the signal far from the sample and close to the sample, giving us a total signal of 0. At each of these temperatures, I can also stop and record the spatial image to see how the susceptibility map develops with the temperature. And so here, each point represents the ability of the superconductor to shield itself from magnetic field at that point. And what we see here is that as we increase the temperature, the susceptibility decreases. But what we gain from these images is that we see that some areas become less superconducting before others. And what we actually see here is how the normal phase, or the less superconducting, nucleates and expands until it covers all of the sample. So the susceptibility signal depends on the temperature. And since we change the temperature in a continuous way, we would also expect from the susceptibility signal to change continuously. And initially, that's what we measured. Here you can see how far from the transition temperature the signal barely changes, but as we approach the critical temperature, it quickly drops to 0. But when we made a more sensitive measurement next to the transition temperature, we found that the signal does not change continuously. When we kept the SQUID close to the sample and slowly increased the temperature, we found that the susceptibility jumped from one value to another. And even more than that, the size of the jump decreased as we approached the critical temperature. So we attribute these jumps to fluxoids penetrating the superconductor, but before I can explain why, I first need to show you how we image vortices in our system. So when I image a vortex in our scanning SQUID system, the flux that I measure from the vortex is spatially distributed. Because of the distance between the sensing point of my probe and the sample, I can't capture all of the field lines originating from the vortex at any given point. Only by integrating over this entire magnetic map, I will get a 1 phi-naught reading. This also means that as the vortex is imaged in our scanning SQUID system, the peak of the vortex does not have, is not 1 phi-naught. So when I increase the temperature, the penetration depth grows bigger and the spatial distribution increases. This means that the vortices become less and less centralized and their peaks becoming less and less strong. And here you can see a plot of the vortex peak as a function of temperature. And at the temperatures that we measured the jumps in the susceptibility signal, we found that the size of the jumps was of the same size of the vortex peak at the same temperature. So when you think about it, this is basically a natural manifestation of the way superconductors shield magnetic field. When you apply magnetic field to a sample, you induce supercurrents, and these supercurrents must flow in closed paths. Therefore, they must maintain flux quantization. So basically, every sensitive susceptibility measurement should detect discrete levels originating from an addition or subtraction of an individual fluxoid. So this behavior is dynamic, and we also see these discrete levels even when we don't change the temperature and we keep all the parameters fixed. So when I measured my sample close to the transition, I started seeing horizontal streaks appearing in the susceptibility map. And these streaks are actually how the signal changes abruptly in the middle of the scan. But this change is not on the same position on the sample. And I wanted to see if the same position on the sample can exhibit two different values of the susceptibility at the same temperature. So I parked my SQUID over one of these recorded streaks. And when I measured it as a function of time, I found that the signal does fluctuate between two different values. These are actually how the superconductor fluctuates between two different abilities to shield itself from the magnetic field that we apply. So these are thermal fluctuations where we keep the superconductor close to the transition temperature without crossing it, and the horizontal streaks are how we image these fluctuations in the spatial image. And just to remind you that there is no circular sample here or something, just that the way the superconductor shields itself from magnetic field. When I repeated these measurements at several locations, I found that the times between the switching events changes considerably. So here you can see it ranges from several minutes to several seconds to tens of milliseconds. And this is a bit surprising because we're talking about niobium, which is a plain, regular superconductor. Also, when I measured the susceptibility far from, in areas that are far from the transition, I found that there is no switching events. And this could be explained either because the magnetic field that we apply was not strong enough to penetrate the superconductor, or because we did not measure long enough to see a switching event. So in addition to the direct measurement of the susceptibility, we could also measure the flux dissipation and use it as a tool to analyze the behavior near the critical temperature. And we can do this by measuring the out-of-phase component of the susceptibility. And in our system, we can measure both the in-phase and the out-of-phase simultaneously. So while the in-phase component, the real part of the susceptibility, gradually starts from 0 at the transition and goes to high values far from the transition, the out-of-phase shows the most activity near the transition. Also, the in-phase and the out-of-phase follow the same structure as they evolve with the temperature. So it was not surprising when we found that the out-of-phase component also shows this modulations, fluctuation. But as it turned out, following the out-of-phase component was more easier to follow these fluctuations because it showed higher activity near the transition. And actually, in another project in our lab, we managed to follow that method and image quantum fluctuations near the superconductor to insulator transition. So to conclude, I have showed you how we use a scanning SQUID to directly image thermal fluctuations. And the related findings from this are that the susceptibility changes in discrete sets, that we found a sample with a large time variation in a single sample, and that these fluctuations also appear in the out-of-phase component. And I would like to finish with an honorable mention of my lab mates, and thank you all for listening.